Hello everybody. Today's first presentation will be about Qubes OS on modern AMD platforms. So a short description of the agenda for this presentation. Firstly, I will introduce myself. Who am I? What am I doing? What I'm interested in. And then I will move to the Qubes OS on this Supermicro super server platform, which I have tested the Qubes OS on. Then I will shortly describe you the modern AMD security features introduced in recent EPYC and Ryzen processors. And then when we will have enough insight about these features, I will describe the status of the secure memory encryption and secure encrypted virtualization on Qubes OS, the status of this feature and open source, whether it is supported, whether it can be used in many of operating systems and Qubes OS, and how these features can involve with Qubes OS and how it will, what impact it will have on its future, and how the future on the AMD processor will look like with Qubes OS. And then at the end, we'll have a short question and answer session. So I am Michał Żygowski. I'm a firmware engineer and technical leader at fwupd Embedded Systems Consulting. I'm also a coreboot core developer. I maintain Braswell SoC, PC Engines, Protectly, and Libertent platforms. Recently, I have also merged support for the Optiplex platform. So if you have any questions regarding these platforms, be sure to contact me. You have all the possible social medias on the left with links. I'm mainly interested in advanced hardware and firmware features, the core boot itself, and the security solutions. So in order to present today's presentation, I have selected the Supermicro super server board, which contains AMD EPYC embedded processor. I have especially chosen this model because it supports the secure memory encryption and secure encrypted virtualization, which will be the main topic of this presentation. I do not advise to use this board in production environments since this board contains a baseboard management controller, which provides a remote access to the machine. It is against the security best practices that Qubes OS offers, and it weakens the security overall. So yeah, for the purpose of this presentation, it occurred to be useful to use the BMC because of the remote work we are conducting right now during the COVID pandemic. So yeah, the installation of release version of the Qubes OS went quite smoothly, and I hadn't much problems with it. However, due to the presence of the BMC and having only a single USB controller, I was not able to create this USB cube. Okay, but yeah, despite the initial launch of Qubes OS was successful, I have encountered certain issues with running the Qubes OS. First of all, in the Zen dmask, I saw many issues and error messages regarding the APIC and some interrupt vectors. Not all CPUs were initialized correctly. There were even messages with, for example, inconsistent MTRR settings. And what was the most significant for me, that the USB controller entered some bugged state, and I couldn't, for example, enumerate any USB sticks that were connected. The issue was also present after reboots, and it basically couldn't boot from any USB, even under the BIOS. And whole the DOM0 dmask was spammed with USB errors. Considering the above issues, I decided to move to the newer Zen, since the release Qubes contains quite old version of Zen, which may not include the support for newest AMD processors. So I asked Marek Marczykowski-Gorecki for some nightly Qubes builds. But before we proceed further, I will shortly describe you the features of the modern AMD processors. And one of these features is secure memory encryption. What does it do? It basically encrypts the DRAM content. So it can prevent from memory code boot attacks. So if one just takes out a memory module, take the nitrogen liquid and try to freeze it, it can later, for example, read all the DRAM contents and, for example, leak the very sensitive data. This feature allows to encrypt the DRAM content, but from the CPU perspective, the content is unencrypted. I will show you how it works on the next slide. So the SME, secure memory encryption, divides basically into two variants. There is a simple SME and transparent SME. Transparent SME is an option that can be enabled on BIOS level and enables memory encryption, whole memory, without any interaction from the software. Thus, it is called transparent to operating system, because it doesn't involve any software to operate. It just encrypts all DRAM, and that's it. But how it works from the CPU perspective. So there is a so-called C bit, which stands for an encryption bit, which indicates whether a given address in memory shall be encrypted or not. The encryption is transparent to software and CPU because it is decrypted on the memories and encrypted during memory writes. And the C bit controls the encryption. So basically, if we have the simple SME, it is dependent on software whether to give an address shall be encrypted or not. So this is the advantage of using the SME instead of the SME. However, the support must be present in the software. And yes, as I said, certain parts may be encrypted and maybe not. For example, guests may have some shared virtual pages, for example, with hosts which shouldn't be encrypted, but the rest of the memory, for example, may be encrypted. And the C-bit controls which parts are not and which parts are encrypted. Another feature which involves the memory encryption is called SEV, Secure Encrypted Virtualization. It is quite orthogonal to SME, thus it cannot operate simultaneously, but it is required to have SME in order to enable SEV. Because SEV also encrypts the memory, but it encrypts the memory for the Quest virtual machine data and code. It is used to protect against accidental data leaks from the Quest to hypervisor. It has additional two extensions, which are called SEV-ES, the encrypted state, and SEV-SMP, the secure nested paging. The SEV encrypted state extends the simple SEV to provide additional protection by encrypting the architectural registers for even strict Quest protection. It was created to protect from malicious hypervisors. Another extension is the secure nested paging, which builds upon the SEV-ES to provide even more Quest security mechanisms and reduce the trust needed in the hypervisor. If you want to protect from the hypervisor or malicious hypervisor, one should leverage all these features. So the secure nested paging is providing following features: VM privilege levels, additional privilege levels that are available for Quest virtual machine, which allow to use certain privileged functions and instructions inside the Quest virtual machine without any intervention from hypervisor. Interrupt injection restriction. There are restrictions into the interrupts that can be injected into Quest virtual machine by the host or hypervisor. There are also memory page protection from corruption, data replay attack protection, and memory mapping and aliasing attacks protection. These are created to ensure the integrity of the Quest virtual machine and its memory and data. So how these features can be leveraged by Qubes OS? While secure memory encryption does not give any particular protection for Qubes OS, except this cold boot memory attack protection, Ceph may be quite useful. However, one must take into following aspects into consideration. First of all, AMD encryption features, so both SME and Ceph, strongly rely on the AMD Security processor. On the newer systems, AMD systems, the AMD Security processor, or also known as Platform Security Processor, PSP, is very tightly coupled to the memory controller. At the boot time in the firmware, it is responsible for memory initialization and managing the memory encryption keys for the SME and Ceph. It is also up to PSP to accelerate the encryption and decryption process during the RAM reads and writes. PSP or AMD Secure Processor is very similar to the Intel ME. It also is present on the chipset. It runs also closed source firmware, and the CPU cannot properly operate without it. Additionally, Ceph requires its own firmware, which is loaded by the Ceph driver. Yet another example of security by obscurity, which is often present in x86 architecture. For those who are quite familiar with firmware ecosystem, then they know that we have already many blobs involved in the boot process on x86 architecture. For example, we have the Intel ME, we have Intel FSP, we have AMD AGISA, we have the PSP firmware, etc., etc. So basically, this is a compromise of including another blob to have more security, or just not using it and keep your operating system as open as possible. So, as I mentioned earlier, I tried the nightly Qubes OS build of the 4.1 version and tried to check the Ceph support status and on Zen and Linux kernel. So the build contained the Zen 4.13.0 and Linux 5.4.31. And the AMD EPIC, I ensure the AMD EPIC processor will support the SME and Ceph and CVS. So I checked the BIOS setup, enabled the memory encryption, and increased the Ceph ACIDs number. The ACIDs are responsible for controlling the ID of the Quest VM, which should be encrypted. Each different ACID is responsible for managing different key of the VM. So basically, each ACID is a count of the parallel Quest virtual machines that can be supported with different keys simultaneously. But despite that, the DMESC of DOM0 contained still some errors that Ceph failed to init. I have found an issue about it for the exact same board, and it occurs that the Linux kernel doesn't enable the Ceph by default. So the option has to be enabled at the BIOS level. However, I haven't found any options in the BIOS to enable Ceph explicitly. So I was left to tweak the kernel and recompile it. Otherwise, I couldn't use the Ceph. However, after some discussions with Zen developer, it occurred that Zen hides the features it doesn't support from the DOM0. So I couldn't even detect the support of the Ceph and SME under DOM0. I also tried to add the KVM AMD Ceph option and memencrypt option to the kernel command line. However, it didn't affect the operating system operation. Okay, so I did also some research of the Ceph status in open source. And yes, it is possible to run Ceph-enabled quests currently with open source tools. AMD has a few repositories which may be found in the references below. And also AMD prepared a guide how to launch Ceph quests. So the requirements are as follows. You have to have libvirt at version 4.5 and QEMU at least of version 2.12. Additionally, SUSE Linux Enterprise Server already natively supports SafeQuest. Moreover, Quest must run OVMF. OVMF is a simple distribution of EDK2 used for virtualization purposes. So it's a UEFI firmware file which can be used in virtualization. Those who know the virtualization environments may know that also CBIOS is such a firmware which can be used to launch virtual machines. However, CBIOS is not currently supported. Also, in order to have Ceph working, hypervisor and Quest must support the Quest host communication structures. These are used to exchange information between the Quest and hypervisor. The Quest must initiate the GHCB structure, which is parsed by hypervisor. It is done because the SafeES, the encrypted state, makes the registers undecodable by the hypervisor due to its encrypted state. So hypervisor cannot dedicate what happened to the Quest OS has. Quest must support creation of such structures to tell the hypervisor what to do and what happened. Additionally, there are certain limitations about intercepting certain events by the host. Due to the encrypted state of these registers, hypervisor cannot intercept all the events. AMD also created a new exception, which helps in the operation of the Ceph Quest. And Quest must also implement the handler for this exception instead of hypervisor in order to tell hypervisor what action to take. Additionally, AMD created a new exit reasons from the virtual machines called automatic exits and non-automatic exits. Automatic exits are typically the events that caused VM exits before and its behavior didn't change that much. And there are non-automatic exits that require certain actions to be taken by the Quest and also the hypervisor. It also involves the handling of the VC exception. So to sum it up, there is still quite much work to do on the Zen side to support Ceph Quest. The restricted event intercepting, automatic exits and no-automatic exits, the Quest host, communication structures, PSP driver, etc., etc. Additionally, Ceph introduces a new API to the firmware, the Ceph firmware, and the Ceph SNP introduces a new API. There are certain new instructions and certain new structures that has to be implemented in order to SNP to work properly. It also has to be implemented in Zen or Linux. Additionally, I got an information that there is currently no AMD Zen's maintainer, which also postpones the implementation of these new features in Zen. One must know that using the SME or Ceph hits the performance because the encryption and decryption process, despite it is accelerated by hardware, it also takes time. So the interface with the RAM is slower than when we are not using the SME or Ceph. And high-end cloud solutions, it may not always be acceptable for all users. For example, to have the resources limited performance. So it is up to the user to decide whether to use or not. But one must be aware that performance may be lower, will be lower. And of course, Ceph is already available Linux kernel, but only for KVM quests. As I have stated here, it can be launched by QEMU. So how these features may affect the Qubes? I think that encrypted Qubes may be used for most critical applications like Vault, Cube, personal, or work. If you want to keep our data safe in VM and protect from malicious hypervisor, it is quite a good solution. Also, Qubes could add optional support to launch a virtual machine using the OVMF with enabled Ceph. As far as I have researched, the CBIOS cannot be supported since Ceph requires PAE or 64-bit mode because it is a requirement to control the Ceph, but CBIOS is a 16-bit environment. Those who already have the secure memory encryption option in BIOS can utilize transparent SME feature in Zen and Linux right now, because you just need to enable this BIOS option and happily enjoy the memory, encrypted memory, and be safe from cold boot memory attacks. That will be everything for my presentation. Thank you, and please ask questions.
Yeah, thank you, Michał. That was great. So yeah, I believe probably first good question would be to Marek. And what do you think about the proposal of use of SEV in Qubes OS? Like, do you see any other use cases than Michał presented, or do you see any other opportunities? And second thing, like, I believe like by default, CBIOS is used instead of VMF, which means probably the migration to OVMF for all VMs should happen soon. I don't know, like, what's your take on that?
Okay, so regarding CBIOS versus OVMF, there is already experimental support for OVMF. We do not focus much on this because all the operating systems we need also support BIOS, and we already also so it's not the top priority for us, but there is already some work in progress. So if some feature would be blocked on the OVMF support, that is possible to finish that implementation. So this should not be a problem. Regarding use cases, generally it sounds quite useful, especially if you can fully protect a VM even from malicious hypervisor. For that, we would need some measurements, like the guest ability for guest to somehow confirm it is indeed running with encrypted memory, encrypted state, and prove that to, I don't know, some external entity or some TPM to release some encryption keys or something like that. This could be really useful because if that works reliably, then we can remove a huge part from the trusted code base, the hypervisor. There are, of course, some technical issues with that. For example, right now we use Zen, and currently it works only with KVM. So there's quite a bit of work to get it working. But I think that could be some improvements. I have also some more questions here. Regarding this transparent encryption, is it possible for the operating system to verify the current state, like if it's to show to the user if it's enabled or not?
Michał?
Yeah, so yes, of course, this is possible. The state is reported via CPU ID and the MSR sysconfig, if I recall correctly.
Okay, so that could be a very first step to just show to the user if it's enabled by the firmware, if it's active or not. Just that should be quite simple if it's possible from the OS to verify that state. But also, how does it protect together with system suspend? Is there some integrity protection during suspend, or how is it handled?
I think it is everything handled by the PSP. So when the system is going to suspend, it is following the normal path, suspend path, and then the PSP is responsible for resuming. So I think the resume is even done via SMM, if I recall correctly. So we are totally dependent on the PSP.
Yeah, that's also kind of issue because it's hard to audit PSP. Yes.
Like I said, it's a compromise.
Yeah, but I assume like Zen probably is more closer to SGX, to leveraging SGX, and this is not exactly apple to apple comparison, definitely, but isn't this the same problem with SGX?
SGX is purely about user space applications. You cannot encrypt the whole virtual machines. And regarding system suspend, SGX does not protect against it. So all your encrypted applications that are running, if you suspend the system, they will stop working. They are simply removed from the memory. Encryption keys are erased. So it does not survive suspend. You need to load the enclaves again.
Okay, got it. Okay, so from your previous answer, I understand that SEV makes sense only in light of some SRTM. So we can seal some key and have measurement during boot of VM to make sure that we are in that SEV is correctly enabled and everything is fine. And only in this light, the SEV may be really useful for Qubes VMs.
Yes, I think so. Because otherwise, from the VM point of view, you cannot really ensure if the encryption is enabled or not, if you don't have some cryptographic method to verify that. And without that method, it's not much better than trusting hypervisor to protect your memory. So yeah, that's correct.
Mm-hmm.
Regarding performance impact, is it how large is it in practice? Do you know?
I haven't found any particular information, and to be honest, I haven't searched that in correct numbers.
Okay. I know some numbers for SGX, and it also really depends on the workflow, because in SGX you have the encrypted memory is quite limited, like 128 megabytes or something like that. So if your application is bigger, you have a lot of swapping between this automatic encryption RAM and normal pages that are encrypted with by ME, which means if your application is small, it works quite well, like there is few percent impact, but if your application is big, then the performance impact can be like factor of 5 or 10 or something. It's really getting really slow then. So I'm just wondering how it compares to AMD implementation. Okay.
Okay, so I see that we have like first comment from Trammell, and he said like SEV does not depend on SRTM other than the PSP. Yeah, I believe like we agree on that, but we more talking about VMs and SRTM for VMs.
Yes.
Yeah, and Trammell said that it is supposed to be secure against subverted firmware. Mark, have you got any comments to that?
How is that? You need some if you without some SRTM, I don't know how to verify that initialization is done correctly. How does it work? because otherwise you need somehow to trust that initialization is done correctly, and also you need to verify if you are running on the real encrypted hardware and not emulated encrypted hardware, like the same feature emulated by QEMU or something.
Mm-hmm.
So yeah, I guess you can. Yes, you definitely can start a VM that with SEV as enabled, but without some method to prove that, it's not that useful, I think.
Yeah, I also like, so Trammell pointed to the trmm.net/SEV, where there is discussion about attested launch, SEV attested launch, and yeah, we should definitely look at it and if this can be leveraged in the VM world, like in Qubes OS.
Yes.
So thanks. So Trammell, thanks for that comments. Any other questions? Thoughts?
Frederick, I cannot hear you if you are talking something. Still nothing? Okay, in the meantime, I have one more question about the host system protection. So SEVS is mostly about protecting VMs. Is it also possible to protect the host system, like in the KVM architecture, the host system is special?
When it comes to host system, the SEV requires in the virtual machine structures, when we have the virtual machine structures to launch a virtual machine, there is a bit that indicates that SEV should be enabled. So we have to be in virtual environment, so any bare metal kernel or anything like that will not work. So it enables the SEV via the virtual machine structures.
Okay, so is it also for the host system there, right?
Is the sound working now?
Yep.
Yes. But just a question, maybe a Jumi one.
We hear you. Yep.
Yeah,
sure, Frederick.
Yeah. Do you think it's possible to enable some kind of on-demand of this feature or not? Because, for example, if you want to protect some VMs, like you said, like work or vault, and etc., there is some VM like build, for example, you don't want to have some performance issue. So, do you think it would be possible to adjust somehow we can allow or not some encryption with this feature? Because if I understand, it's at BIOS level, so maybe it's not
on the BIOS level, you can enable the memory encryption itself, so whole memory is encrypted.
Yeah.
You cannot choose anything when you enable on the BIOS level. However, if you let the software decide which parts shall be encrypted or not, you have to let the SME to be enabled by the software. Then the software decides which pages, memory pages, for example, shall be encrypted or not. The CBIT controls the encryption.
Mm-hmm.
But when it comes, for example, for the CEV, it's up to the hypervisor that decides whether this virtual machine shall be encrypted or not, for example, to use the SEV or CAVES.
Okay. Because we have, for example, we can also imagine another case like in the near future to have some cubes in the cloud and having some admin VM that we trust somehow. And we said, okay, I want 1, 2, or 3 VMs with such encryption or not. I think that could be maybe useful. I don't know. I'm just thinking of a future case.
Yeah, it sounds interesting, but I believe like the key problem we have is we don't have Zen support. And Marek, if you can like evaluate or just throw a number, how big this would be.
Actually, there are some people interested in also running Qubes on top of KVM for a different reason, because KVM have much better hardware support, and especially other architectures like Power or RISC-V. It already works on KVM, but not with Zen. So having Qubes on KVM is not totally impossible. And in fact, some parts are already developed. For example, there is a Vichan library already done. I don't want to give some exact numbers or dates or something like that, because it's a huge project. But it is in progress, I would say.
Yeah, it would be interesting to know how this effort can be supported, or how community and 3M Dev maybe can push that forward. I believe if KVM like already enables a couple other architectures, that's very interesting, and couple additional features, then it is very interesting. And especially that it looks like developers seem to choose KVM for enabling new stuff. So SEV is in KVM, not in Zen, as well as RISC-V, as Power. So do you have any kind of information how community could participate and help in moving KVM support for Qubes OS forward?
I think the biggest obstacle with Qubes on KVM is reducing trust, reducing data processing in the host system. Like with the KVM, KVM assumes all the device emulation or the backends are running on the host. Stuff like network, the actual network hardware is connected to the host system, and the host system is responsible for routing network. Same for disks, same for graphics and stuff like that. And this is something that we want to change in Qubes. Like currently we have with Zen, QM is related in stub domain, no network interfaces in DOM0, only in USB in sysnet domain. So those are features that are currently hard to do on KVM, and are the first thing to solve. Other than that, we already have quite a bit abstractions, like we already use libvirt, so starting and stopping VMs should be quite simple when migrating to KVM. Someone already implemented a Vichan library, so I think the most tricky part right now is this device emulation and network connections between VMs.
Okay, where people can help, like where, like in terms of, I know the tasks, we know the tasks, but how to engage in that?
Currently, I think the most coordination is done on the GitHub issue. There is one about PowerPC support, and it's mostly about adding KVM support in practice. Actually, I probably should clean up that.
Okay, got it. Like I know that issue. I believe like this is the one with the 2 Bitcoin bounty.
Yes, this one.
Okay. Okay, any other topics, any other questions? Like, I believe we have 15 minutes to next session. We can start earlier, but I would like to take a like 5 minutes break for everyone. And we like, if there are no more topics, no more questions, then in 5 minutes we will start next session about LVFS. But maybe there are other like suggestions. Yeah.
Yes, I have one quick question on the practical matter. The SEV requires some extra firmware besides PSP firmware, right? How is it loaded on Linux? Is it a separate file you need to provide?
Yes, it is a separate file, and it is a part of Linux firmware. The Linux firmware repository.
Okay, thanks.
Okay, so Norbert, you can kind of switch to 5-minute break, and let's get back like in 4:51, and let's continue.